My name is Jason Deveau. I'm the Application Technology Specialist with OMAFRA. Today I'm going to present our pass coverage, drift, and efficacy using Deveau Complete in Field Corn. This is work that we did in 2022. So acknowledgements up front. We'd like to thank Adam Pfeffer and Bayer and the volunteers that helped make the work possible. Adrian Rivard, who's the principal with Drone Spray Canada, the grower cooperators that gave their fields and sprayers and corn for the work. And when things got really tough, Amy Shee, who gave me statistical support and showed me that I really need to go back and do more stats. There is increasing demand for corn spraying in North America. There is a lot of concern about invasive insects and new diseases, not just gibberella ear rot, which maybe we're all familiar with, but increasing incidence of tar spot, particularly in Ontario. And we've learned that product choice and application timing and variety choice can all help protect corn. But there's also a lot of interest in evaluating new application methods of crop protection products. Maybe it's how we're spraying them, not what we're spraying and when we're spraying. And traditionally, we have two methods of applying products to corn. We have ground rigs like the field sprayer on the left, and the pros of using this method is that the timing is flexible. If the grower owns the equipment, they can go out when the conditions are conducive to a good spray day. The product choice is flexible. They can put on what they feel is going to be best. Their water volumes and the spray quality they choose to use are under their control. They can get corner-to-corner coverage if they're willing to take the time to negotiate the boom into some of the fiddly corners, and they can adjust any of their sprayer settings to fit the conditions. Now, if you go with an aerial system like this helicopter, you can get it done a lot faster. It's a higher work rate, and the liability is no longer yours. You didn't do the spraying, somebody else did, and you certainly don't have to worry about capital investment because you didn't buy the helicopter. And just as an added bonus, it's compaction and trample neutral. No damage to the corn by driving through it, no damage to the soil by driving on it. But there are cons. The field sprayers are slower, certainly compared to the aerial systems. And as I mentioned, you do have tram lines. There are compaction and trample concerns. And with the aerial systems, maybe they're not there when you want them to be there. There could be scheduling concerns. Everybody tends to want the application at the same time. Perhaps there's a limited product choice. Some chemistry is labeled for ground rigs and some is labeled for aerial, but not necessarily back and forth. You have limited water and spray quality choice. Most of the aerial systems spray 5 gallons per acre, not perhaps the 15 or 20 or more that the field rigs put out. And spray quality is more about getting the product to the corn, more so than the coverage when it gets to the corn. There's also the public perception. You can see a lot of spray coming off the helicopters and people instantly think drift. Not to say that they're not right or wrong, but certainly drift is a concern with the helicopters, just the visibility of it. And field accessibility. Perhaps it's hard to get a helicopter out there, plus the filling station. Maybe there are physical obstacles like hydro lines or tree lines that make the helicopter a harder choice. And then there's the new kid on the block, the drone or the RPAS. RPAS is Remote Piloted Aerial System. There are a lot of acronyms, we'll just say drone. With the drones, like the field sprayer, you get flexible timing. You get corner-to-corner application. It's a minimal investment, perhaps $10,000, $20,000, depending on the size of the drone, versus $750,000, depending on the field sprayer. Again, it's compaction and trample neutral, and they're fun. There's an excitement factor about drones right now. But there are cons. It's a very low work rate, lower than the other two. Just like the aerial systems, you're limited with the spray quality and the water volume you can use. And perhaps this should go up front, but in Canada, we don't have any registered liquid pesticides permitted to be sprayed by drone, at least not at the moment. So any of our experience is strictly with research. And there's a fundamental lack of understanding on how to use these devices correctly. It is not as easy as it looks. This isn't just a field sprayer in the sky. There are a lot of interesting variables that no other form of application has to contend with. So what did we do? We had three objectives for our study. First, we wanted to quantify spray coverage in field corn at three depths. That is, how much coverage do we get at the top, in the middle, and at the bottom of these large 8-foot deep canopies. And we didn't want just the upward facing surfaces. We wanted the downward facing or underleaf surfaces as well. So we looked at adaxial, that's top, and abaxial, that's bottom surfaces. And what do we mean by quantifying spray coverage? There's a lot of different ways to define spray coverage. So we looked at it three different ways. First is a pesticide residue, which is fairly traditional with a uh, a research project where we're looking at coverage, but we didn't just say how much product we found. We indexed it to the percent of the applied rate per acre. What that means is if you put out 20 gallons per acre, how much of that 20 gallons per acre as a percentage did we find on so many square centimeters of leaf? We also looked at coverage as area covered, which is to say how much of that surface actually received a deposit. Maybe 10, maybe 15% of the surface got spray coverage. And finally, we looked at deposit density. And it sounds like we're splitting hairs, but this time we didn't just look at how much product ended up on an area, we looked at how it was distributed. Maybe it wasn't one big droplet on a leaf. Maybe it was 30 smaller droplets spread evenly over the surface. And when it comes to something like a contact fungicide, that distribution of spray matters perhaps as much as the dose that the leaf received. So it's not just a matter of getting one big blop of spray in the middle of a large target. If it's a contact product, it matters that it's spread fairly evenly over that surface. So three different ways to look at coverage. We had another objective, and that is to look at drift. Uh, we didn't just want to see how much product ended up on the crop, we wanted to see how much blew away. So we quantified drift from pesticide residue again as percent applied rate per acre using horizontal flux. What these are large 8-meter high poles with a string hanging off of them. And as the spray leaves the application equipment and blows with the wind, it transects or passes by this string that's hung from 8 meters high. And then we're able to lower that string meter by meter, collect it, and look to see how much residue is at each meter of altitude. So this is a little different than how a lot of drift studies are done. They tend to rely on ground deposition, samplers that are put on the ground up to 130 meters downwind. We chose this method because we could plug these poles right into the corn, right at the edge of the swath, without having to mow down 128 meters of corn on the downwind side. Finally, we wanted to look at efficacy. So we could identify how much coverage we got, we could identify how much drift we got, and then did the product actually work? So we wanted to evaluate the efficacy of Deveau Complete, which was the Bayer product we used in these trials. We applied using a drone at 2 and 5 gallons per acre, and we compared that to a conventional overhead broadcast treatment from a field rig of about 16.7 gallons per acre. So does the drone work as well as a field sprayer? So here's the equipment settings that we used. The overhead broadcast treatments, we just went with what the grower typically did, to be realistic. In this case, both growers in both fields that we worked in did 16.7 gallons per acre. The first person used T-Jet extended range 11006s. They drove at 10 miles an hour. And in the first field, we used a John Deere rear-mounted boom with pulse width modulation, or the exact apply. In field 2, just to get a good cross-section of ways that growers apply, we used the sprayer in the picture here. This is a New Holland. This is a front-mounted boom. It wasn't pulse width modulation, but again, it was T-Jet XR 11006s. Now, there was a third field in the mix here, and this is a bit of a pet project, so I'm not going to spend a lot of time on it, but rather than use a classic overhead broadcast application, we wanted to try drop arms or drop pipes. They go by a lot of different names. So this is our directed treatment, and we traveled at about 4.5 miles an hour. We sprayed 20 gallons per acre using pretty misty 110-15s. But what's neat about this is the nozzles are suspended inside the canopy on the row centers or the alleys. And this is just a car wash. You simply can't miss. You get 100% overlap in the corn zone. That is the 3 ears of corn that we were after, particularly after the tassels. I'm sorry, the silks. So 100% overlap from these 110s in the silking zone. And here's an image of a different way to hang them, but you can see that it makes quite an impressive cloud suspended inside the canopy. Finally, the drone. We chose to use the DJI Agris T10. This carries 8 liters, and it took about 8 or 10 minutes per flight time. The pump is capable of 2 to 5 gallons per acre. You can really only run O1 or up to O2 nozzles on these, and they can fly anywhere from 2 to 7 meters per second. The way we used it is we put AIXRs, these are air induction nozzles, O2s, plus a 50 mesh screen. We flew it at 2 meters above the tassel of the corn. We flew at 3.5 meters per second, spraying at 45 psi to get 5 gallons. And we flew very quickly, 7 meters per second and 70 psi to get down to the 2 gallon per acre we were shooting for. Of course, because this was a research allowance, or we had an RA for this, we did a calibration check to ensure all our nozzles were putting out what we expected, and we confirmed our speed using RTK GPS, again, to ensure that we were flying at the speed we thought we were. Now, this is where using drones is a little different from any other kind of application. If you've got a 120-foot boom, you can assume a 120-foot swath. If you're flying from a helicopter or a plane, a manned aerial application, there's a series of tests that you do, fly-ins, to determine how big a swath you can expect. But we really had no sense of what the drone was capable of laying down. So one of the first things we did was go out in the evening and fill it with a tracer dye, fly at different speeds and different altitudes, and then using black lights, go and see how far we saw spray drift, or in other words, what the offset was from the prevailing wind, how much blew laterally and how much landed under the drone. And this was very telling, and it gave us the loose outline of what we could expect. But it wasn't terribly quantitative, so we had to use something a bit more conventional. This is the swath gobbler, and it's quite new, but it's based on some old technology. What this is receipt paper, and it's laid out perpendicular to the path of the drone. It's AB line. The drone flies at a certain speed and a certain altitude, spraying food dye, in this case blue number 1, same thing you'd find on M&Ms. And then we have a camera and a spool that reels in this receipt paper, photographing it moment to moment, and it spits out a histogram telling us how many drops per square centimeter and how much coverage we got at what point along the path of the drone. All of this to give us some sense of the coverage along its path or its swath. And just because we wanted to be absolutely sure, we used a more conventional technique. This is what an aerial fly-in would use. This is based on Operation SAFE, which is an established protocol for determining the effective swath width from a plane. Basically, you just lay out water-sensitive papers perpendicular to the flight path. You fly into a headwind, and you retrieve the papers, digitize them, and determine how much spray went where. Now, if you get 10 people in a room and ask them how to analyze swath, you're going to get 10 different answers. But this is the method that we used. It looks complicated, but it isn't. We graphed out the percent coverage in each position, and just take a look at the blue curve. And you can see it's a very narrow and high peak. We seem to get a lot of spray pretty much directly under the drone, tapering off to the left and the right, more so to the left, which meant that we probably have a bit of a side wind. And then you have to figure out what the next swath width should be. How far over do we have to move the drone? So this little piece of software that was developed by Dr. Tom Wolfe allows us to plug in our values and then mess with the offset and figure out what the overlap will be. So one of the first things you have to do is figure out how much is enough. So you set that threshold. That's the that's the blue line at the top, the horizontal line. So you figure out, well, you probably got too much directly under the drone. So you back it off by about 10%, and then you start offsetting. Wherever these swaths overlap, you get cumulative coverage. The trick to all of this is you want the lowest variability and you want the most consistent swath without getting too much dose and not enough dose in these gaps. You just kind of want the best spray you can manage. And after several passes, we worked this out to be about 3.5 meters was the most effective swath width, the most consistent swath we could get under this drone at a certain speed, at a certain altitude. All that to say, you can see why calibrating drones is a big deal and why it's still a big lesson. Now, here's some information on the fields that we worked in. I won't belabor this. They were in 3 different Ontario locations. If you care to pause the video later, you can look at the corn varieties. You can look at which rates we applied in which field and which data that we were after. But suffice to say, we tried to keep each location as consistent as possible. Same 30-inch row spacing and corn at the same stage of development, relatively similar environmental conditions, and nothing interfering like obstacles or uh, cedar hedgerows or anything that might throw our work off. This is a picture of our randomized plot. It's a lot to take in right away. You can see that we did 2 and 5 gallons per acres. You can see those labels at the top of the screen. You can see that we left unsprayed checks, and you can see the wider swaths is for the field spray are 120 feet wide, and where we did 16.5 gallons per acre. So those treatments were randomized. These were big fields. They were either 1,800 feet deep or 1,100 feet deep, depending on the location. And those Ritz Cracker Premium Plus Cracker gray squares, these are the arrays of samplers that we set up. And if you just look over to the left, maybe the second block from the left, the 2 gallon per acre treatment, you can see that we set an array of these up about 100 meters, 330 feet into the corn, and then another array, another 100 meters or 330 feet deeper into the corn. We left 40 feet for the swath. It had to fly back and forth. How far? I think it was 3 passes, maybe 4. We left some buffer to either side. Those X's represent the drift poles. The idea there with the horizontal flux collectors is you want them right at the edge of the swath offset. In other words, you don't want to spray them directly, but you kind of want them at ground zero at the edge of the swath because anything they intercept can then be considered to be drift. This was a lot of work setting up all these samplers and taking them back down. It took a whole week. These are the collectors. They were 8-foot high, 1-inch diameter PVC conduit tubes. And the black spring-back clips held these alligator clips that you can see protruding from either side. And on the alligator clips, we had our samplers. The plastic is called mylar. It's a conventional substance we used for residue trials. You can just rinse everything off of them and figure out how much product is in your rinsate. The yellow cards are the water-sensitive paper. When liquid touches them, they go from yellow to blue, and then you can digitize them. And there's software that counts the droplets and determines how much area was covered. So this is just a bunch of poles set up. We were loading all the samplers, and then these were carried out into the field and set up on the array of 9 samplers that I showed you earlier. And if you've never been in corn, it was quite an experience. You had to figure out where's 100 meters. Thank goodness I had a runner's watch on and a GPS. It told me when we reached about 100 meters. We ended up, by the end of the study, setting up 19 of these 3x3 collector arrays at 100 and 200 meters into the field and carrying all these in with the rebar and the mallets and the poles to set them up was quite a task. The end count, we used 1,126 water-sensitive papers. We used 864 Mylar sheets, and some serious lessons were learned about my tolerance for corn pollen, which turns out to be nil. I went in pretty cavalier, just wearing shorts on day one, and quickly learned that Benadryl was going to be my best friend. By the end of the week, I was bundled up in Tyvek and breathers and masks. and it was just the only way to kind of survive it. Here's a peek at the horizontal flux poles. It was kind of like fly fishing. They're big, telescoping carbon fiber poles. You snap these out to their full size. You put a pulley system at the top and set them on these broad four-legged platforms, and that holds them more or less straight up or down. And kind of like pulling a flag up on a flagpole, you've got this cordon that you haul up, and it pulls the string up into place. And these were set, I can't recall, I think 10 meters apart on the downwind side. Here's three of them, maybe more than 10 meters now that I'm looking at this. Here's three of them in situ, and you can see the flagging tape just as a kind of a gut check at which direction the wind was going in. Of course, we did use Kestrel wind meters to make sure we had all our atmospheric data. We set 3 of these up for each pass, and we ended up doing 12 of them in total. On the right, you can see the cord that is the actual sampler. This is boiled, bleached, completely clean nylon string, woven string. Kind of at the last minute, you run this up to the top of the flagpole, and then there's a kind of a ballet after the spray where one person has a baggie and they reel it in 1 meter at a time with a helper who cuts the string at the right positions. So the clean person never touches the dirty string, and the dirty person never touches the clean sections. It's quite a little ballet. I did mention we had field-specific weather data. We collected that at nozzle release height, just like holding a wind meter at the nozzle level on a boom. We tried to set this Kestrel up pretty much right where the nozzle would release, and we ended up supplementing what it told us with field-level weather summary reports from the growers' local weather stations, just to make sure we had the right data. Now, bear in mind, we sprayed Deveau Complete here, so we were looking for efficacy. We loaded that at 8 ounces per acre, but for the residue work, we weren't actually looking for the Deveau. We used PTSA, which is again a standard tracer solution used in residue work. It's very stable, although we did want to collect these mylar sheets as quickly as possible and get them into the cold, so we had coolers on the trucks for that. Here's a glamour or vanity shot of the drone mid-flight. Here's another. If you look, you can see that the downwash, which is one of those unique factors to a drone, no matter how fast they fly, they're always pushing down. And contrary to popular belief, helicopters do not create downwash or wind unless they're hovering. When they're in flight, the corn doesn't move at all as they fly over. They're really no different than a plane. They just drop a blanket of spray behind them. But the corn does tend to push the spray down as it pushes the drop down and pushes the drops, well, frankly, all over the place. And that's why we were looking at drift. Here's part of that ballet as the samplers were collected. You can see Mark Ledeborough, who's the principal with Application Insight LLC out of Michigan. He did the residue work. You just put a baggie inside out over your hand and just start wrapping it around and around till you get a meter. Someone cuts it, and you turn it inside out. There, you've never touched the string, and it's ready for rinsing. The water-sensitive paper goes into this scanner. It's digitized, and as I mentioned earlier, we can determine how much of the surface gets covered and how many drops per square centimeter, or the droplet density or deposit density we get. Now, for those who maybe still don't quite get why we would look at spray coverage in 2 different ways, here's a metaphor. This is a battleship, and if you look at A, you can see we have about 10% of the surface covered, actually exactly 10% covered. There are 100 holes, there are 10 droplets, we'll say. Now, would you say A and B have the same coverage? They both cover 10% of the surface. If I were to rinse that off and just do residue work, they would look exactly the same. You'd rinse the same amount of product off the surface, but you would have lost a lot of very good information about how that spray was distributed on that surface. And if it is a contact product that doesn't move, like most fungicides, and you're after something that's sessile or an ascospore or an insect maybe that doesn't move, you want to make sure you get the best coverage possible and the best distribution. And only by looking at B can you figure that out. And C is just showing that if you do repeated fungicide applications, the odds of actually hitting the same spot are pretty low. So as long as you've left some residue or residual, I mean, from the last application, you kind of have both sprays working for you. If I were to tell you this is the lab where we looked at PTSA, I'd be lying. This is actually a pretty rinky-dink setup I've got for looking at rhodamine, but I didn't have a good picture of the lab for the PTSA work. But needless to say, it is one persnickety process. They monitor temperature in the room. They monitor airspeed in the room. All of this can set their equipment off and give false results because they're actually capable of giving us parts per billion residue. It's very laborious, and I'm really glad I didn't have to do that part. Results. Here's the first thing we learned, and it's interesting for me going forward. Water-sensitive paper has its limitations. There are some things it can tell us and some things it's simply not capable of telling us. And what's interesting is that it's usually faster and easier and certainly cheaper to put water-sensitive paper out than it is to do a full-blown PTSA residue study. And I wanted to know how well they correlated with one another. And it turns out they gave very similar coverage patterns. The water-sensitive paper was lockstep with what the residue work told us. Here is the average percent area of the target covered based on the percent applied. So again, if you spray 100% out on your field, how much could we recover? And on the left, you'll see those three sets of histogram or bars are 2 gallons per acre. On the right of your screen, you see 5 gallons per acre. Let's look at the two. The blue bars represent what the residue study told us. You can see a trend at the top of the crop, the middle of the crop, and the bottom of the crop. There's less and less residue deposited. And this stands to reason. This is a trend we see in all dense canopies. If the spray is being directed from one position, in this case over the top, it gets filtered out as it passes through the canopy. You have less and less spray to deposit. So you see this, I've usually known it with air blast to be exponential decay. But for narrow, shallower crops, maybe it's closer to linear. And in this case, it was linear. You get, say, 100% at the top, 50% in the middle, 25% at the bottom. It just continues to decay. And you see the same trend in the orange. That's what we saw in the water-sensitive paper. When you look at over at 5 gallons per acre, you can see overall we had more coverage. Again, that stands to reason. We sprayed more volume, so there was more spray to collect, but it does follow that same decay from the top to the middle to the bottom of the canopy. Now, we couldn't do a direct comparison between what we saw for residue and what we saw in the water-sensitive paper because it looks as if the water-sensitive paper is less sensitive, but it's just a different way of looking at it. So in order to compare apples to apples, we normalized it. Let's pretend that the mylar at the top of the canopy gathered everything it possibly could. It's 100% coverage. And likewise, the water-sensitive paper, which was at the same plane, also gathered 100%. You simply couldn't miss. So if we normalize everything to the top position and then look at our coverage, we see that the decay is still pretty much the same, and the levels are pretty close. They're off by, I don't know, 5–10%. But given the expense and the nuisance of doing residue work, this shows us we can learn a lot of compelling and accurate information strictly from using water-sensitive paper. So, moving forward, it's maybe not just a grower's tool for double-checking coverage, but something we can milk a little more information out quickly and cheaply. So let's get to the actual treatments. What did we learn from drone versus field sprayer? Well, we learned that the drone and the overhead broadcast sprayer produced similar deposition patterns, which is to say more at the top, less at the bottom. In Sciences, a negative linear relationship between the coverage on the upward-facing samplers was observed. A nice high R squared. That means all the upward-facing mylars and papers showed that decay. And we also learned that getting a droplet to stop in midair, shift left, and go straight up to hit the bottom of a target is still nearly impossible. Even with all the vortices and random movement of droplets underneath the drone, we didn't see a lot of abaxial coverage from the drone in any condition or the field sprayer, which means half of all those papers and mylars we put out were pretty much empty. We also learned that overall, The more volume you spray, the more coverage you get. Again, this is a bit of a no-brainer, but it was nice to see that the drone followed that exact same pattern. The overall coverage shared a direct relationship with the volume for RPAS and overhead broadcast applications. Now we get into the nitty-gritty. Let's start looking at the average coverage, which is to say how much surface received spray. On your left, we have the broadcast applications, almost 17 gallons per acre. As we move right, you see that this is the drop pipes, which spray 20 gallons per acre. We haven't talked about those for a little while, but we will. And then finally, the two drone conditions at 2 and 5 gallons per acre. For each cluster, you can see there's the upward-facing paper on the far left for the broadcast. 22-23% of the surface was covered, and then immediately right to it, a sad, empty little error bar, where on the abaxial or underside, we got nothing. So there's top, middle, and bottom, upward-facing, alternating with downward-facing. You can see it, almost 17 gallons per acre. The overhead field sprayer was kind of the winner for coverage. The directed application, that is the drop arms, it gave pretty decent coverage as a percent area in the middle and at the bottom of the canopy, but it sure didn't do a ton on the highest upward-facing paper. The reason for that is those nozzles were inside the canopy spraying up. They weren't outside the canopy spraying down, so that paper really wasn't oriented to capture that spray. In fact, what this directed application tells us is that the spray didn't fly out of the canopy and then land again. It all kind of stayed inside. The drone, well, didn't do so great, at least not as percent coverage. It is interesting to see that way down deep on the 5 gallon per acre, it looked to do about as well as the directed application at 20 gallons an acre. So big differences in the percent area. What did we learn? Well, we learned that we maybe should have looked at something a bit different. Thankfully, we did. Consider this. The directed applications, that's the drop arms. They delivered a very fine spray quality. That is really fine droplets. And I said they were sprayed sideways from inside the canopy. It gave overall the highest overall. Ooh, did I miss a slide here? No, I just have them out of order. I'm sorry about that. Let's do this first. Let's shift gears. Instead of looking at the percent area covered, let's look at deposit density now. Remember, this is how many drops per square centimeter. The broadcast, which was the shining star, now doesn't look quite so great. It only got about 100 drops per square centimeter on the top, and somewhere around 20, and then 10 as you get deeper in. The directed application, twice or more the number of droplets counted on the top. And if you look, now we have that near mythical underleaf coverage. We're getting counts on the abaxial surface because these droplets are spraying up, not just down, so we're actually managing to hit things. What's interesting is that the drones suddenly don't look so bad. Look at the 5 gallons per acre. In the last slide, when we compared 5 gallons per acre as percent coverage, it wasn't even close to a field sprayer. But if we look at the number of drops per square centimeter, it doesn't look a whole lot different. How is that possible? And the answer is the size of the droplets we used. I'll have to flip these around for the future. The directed application made finer droplets, so we had so many more to count. And the drone made finer droplets, so we had so many more to count. Whereas the field sprayers were using air induction droplets, which are really, really big. So they might get 1 or 2 big splats on a surface that can cover a lot of area, but only in 2 very discrete areas. Whereas the directed application of the drone were capable of peppering the entire surface. And that means that the coverage might not be so far apart after all. For the drones, the spray coverage was significantly reduced when we went from 5 to 2 gallons per acre. Let's just focus on the drones for a second. We had like 60% or 75% less less deposit when we dropped from 5 to 2 gallons per acre. And it didn't matter how we looked at it. Percent coverage, deposit density, residue recovered. It just put out less. No big surprise, I suppose. What was interesting is that when we went to less, 2 gallons per acre, drift went up. Drift was almost 75% higher for a 2-gallon per acre application over a 5. That was a bit of a shocker. We were spraying less volume per acre. How did we get 75% more drift? This is sort of boiling those numbers down a little bit by field and the top, the middle, and the bottom. Again, I'll just put this here if you want to rewind the video and have a look at that. But here's how I prefer to look at it, and it's in a histogram. This is more or less to scale. There's the drone on the right and the corn, which was about 8 feet high. So everything's about to scale. And on the left, the histogram, the 8-meter high pole, this is how much residue we pulled out for each meter. So the blue is 2 gallons per acre, and the red is 5 gallons per acre. And you can see that the blue lines are longer than the red. In other words, there was more residue or more drift intercepted by the string at that altitude than the 5 gallons per acre. And if you were to work out the areas under the curve, you'd see how it's 75% more drift for the 2 gallon per acre than the 5. What happened? How was that possible? Well, we think primarily this was travel speed. When a drone speeds up, it tends to nose down a little bit. It tips forward. So that downwash, that air that it's generating, doesn't just get pushed straight down, but it also kind of gets pushed backward behind it a little bit. And all the spray that gets caught in those vortices is thrown not just down, but sort of behind and up, which puts more fine droplets in the air, which are buoyant and eventually move with the wind. And because we had to boogie, we had to go from 3 meters per second at 5 gallons per acre to more than twice the speed to get down to 2 gallons per acre. We think this is what did it. We also, unfortunately, found a field effect. And we took great pains to make sure these two fields were completely the same. And yet, when we looked at how much drift we got in one field versus another, and how much coverage we got in one field versus another, we saw a significant difference. So compared to field 1, the average coverage in field 2 was about 30% less for 2 gallons per acre and 41% less for 5 gallons per acre. In other words, field 1 got 30 or 40% less coverage. We don't know why at this point. And then we also saw that the field that got less coverage got more drift. So now what's going on? How did we get 75% more drift in one field and 30 or 40% less coverage when they were exactly the same and flown the same way? Here's what that drift looks like if we were to take just field 1 versus field 2. Again, look at the red, so much more drift in field 2, and it can comment a decrease in coverage. What was the difference? Well, we think the difference was the wind. Not only do you fly faster to get down to 2 gallons per acre, we kind of got pinched at the end of this study, and the wind was a little higher than we would have liked, actually a lot higher. In field 1, we flew with maybe 7-kilometer-an-hour wind. In field 2, it was 18-kilometer-an-hour wind, or like 3 times higher. But it was the last day of the study, and we kind of had to get her done. That's the only difference we could find. So let's just put a pin in that for a second. I should address efficacy. This really wasn't my part of the study, but I should report that in the 2 fields we worked in, bad luck, we had no disease pressure. So there was no clear treatment effect. Our unsprayed checks looked as healthy as our sprayed. So, we really couldn't learn whether or not the drone was as capable of protecting the crop and getting us a profit as the field sprayer was. So there's not much I can say about that. There were, however, 5 other fields in this study. I didn't look closely at coverage in those fields. We couldn't do it logistically. Unfortunately, the 2 fields I picked were super clean. In the other 5 fields, they did find disease pressure, and they are claiming that tar spot control was about the same from what the drone did versus the field sprayer. So that's interesting. I can't say whether that's the case or not. I wasn't privy to that part of this, but that is the claim. So what's our take home from all this? What did we actually learn? Well, for the use cases explored in this study, that is to say the drone flown a certain way with the certain nozzles and the certain speed, and the sprayer operated the same way, for those particular setups, we learned that low volumes and high travel speeds are not advisable for drones. especially in high wind conditions. We learned that water-sensitive paper and residue samplers should be used together. They tell us different things about spray distribution and how much dose or product is actually applied in order to get a complete picture. Now, we also learned that water-sensitive paper is pretty capable of telling us a lot on its own, but a complete study would have to use both of these systems, especially if you were using contact products and smaller droplets. We think this study is probably one of the most complete drift coverage studies for drones at present, although there's a ton of research happening right now. And we get new information every single day. But as a mass balance study, which is to say, you drop this much in the field and then you try to find it all, we were actually able to close mass pretty good here. We figured out how much ended up on the crop and how much ended up on the drift lines, and we saw how those correlated to one another. So future work, it would have been really nice to be able to separate the volume we sprayed from the travel speed. As it stands, we ended up inadvertently changing two variables at the same time. When we went from 5 to 2 gallons per acre, we also had to speed up. It would be really nice to just speed up or slow down and spray the exact same volume so that we could tease apart the volume effect from the speed effect, and that way figure out their relative influence on drift and coverage. And that's something we're hoping to do in the future. What's taking people by surprise, I think, is that drones are not field sprayers in the sky. They're not helicopters. They're not planes. I would say the closest correlation between what they're doing and any other piece of conventional equipment we use in spraying is that they're air blast sprayers in the sky. They are using two liquids at the same time. That is the liquid you're spraying and the air that they produce. And the ability to control the air separate from the liquid flow should allow a user to dial in an optimized application. The other side of that coin is if they don't control both fluids, they could end up inadvertently doing the wrong thing, creating too much air or a drift situation or blowing past a target. So more understanding is required on how to dial in a drone to get the optimal air effect and the optimal droplet size and volume to achieve whatever they're hoping to achieve for a given canopy. And we wrote a book on this a couple years ago, Air Blast 101, and I think it's going to start to have, it's going to bear relevant information on how drones function. And if you want to see this study, we're shooting to get a crop protection article published, but eventually it will land on Sprayers 101. Thanks for your attention. I hope that wasn't too much too quickly. If you have any questions, you can reach out to me.